start a recording. So ANSYS 2023 R1 come down to mechanical APDL product launcher. Create a unique working directory. So section 2, we'll call this assignment 2. Set that folder, and then for the job name, call it assignment 2. All right, that's going to be the prefix for all the files it generates inside that working directory. All right, so once you got that, click Run. If you typed in the prompt to create a new folder, it'll ask you, do you want to create that folder? Just click Yes. All right, here we go. So let's create our 2 elements that we need, element types. So we need link 180 for all the 2 force members, and then we need this 3D mass element to account for the mass at the end there. All right, so again, we're going to lump this into a single mass, put it right at the origin. All right, so go ahead and go to preprocessor, element type, click Add, Edit, Delete, and then click Add. And the second option down there in the middle window says link. And on the right-hand side, we want the 3D finite strain 180. So that's element number 180. And then click OK. You should see type 1 link 180 here. Click Add again. And then click on the first item in the middle window there, structural mass. You get 3D mass element number 21. And then click OK. Click Close. And let's go up to the prompt here, the command prompt up top. And let's read about these elements. So type help, comma 180 in first. Click Enter. So we can quickly read just a little bit about this one. So link 180 is a 3D spar used in a variety of engineering applications. The element can be used to model trusses, which is basically what we're modeling, a truss type structure. It's pin joints, 2 force members. You can also model sagging cables, links, springs, and so on. The element is a uniaxial tension compression element with 3 degrees of freedom at each node. Translation, the X, Y, and Z direction. The tension-only, cable, and compression-only gap options are supported. As in pin joint structures, no bending of the element is considered. There's no bending stress. There's no shear stress on this. Plasticity, creep, rotation, large deflection, large strain capabilities are included. So here's an illustration of the image. So we have 2 nodes, node I and node J right there. And again, these nodes can only move along the axis, and the force is only along the axis of the element, similar to what we've been doing in lecture. If you scroll to the very bottom, sometimes it's useful to read the assumptions and restriction. We can read a couple of these. The spar element assumes a straight bar, axially loaded at its ends, and of uniform properties from end to end. The cross-sectional area must be greater than 0. That's good. Displacement shape function implies a uniform stress on the spar. So again, this kind of goes back to the 2 force member. Stress is simply the force along the axis divided by the cross-sectional area. That'll give you the stress, and then that stress is uniform throughout the element. Maybe just read one more here. To simulate the tension compression only option, a nonlinear iterative solution approach is necessary. That's a little bit different than what we'll be doing in lecture. We directly solve by taking the inverse of the matrices, the displacements. Here, if you're going to use its tension compression, it's actually going to default to an iterative approach to try to solve the displacements. Okay, let's go back to ANSYS. Let's type help, comma 21, and take a look at the mass element. So mass 21 is a point element having 6 degrees of freedom, translation X, Y, Z directions, and rotation about the X, Y, Z axes. A different mass and rotary inertia can be assigned to each coordinate direction. Here's an illustration of the element. So when we make this element, we're just going to click one node. We don't need 2 nodes, not between nodes, it's only at 1 node. And we'll give it a mass in each of the 3 directions. And we have the option to give it an inertia, but we're just going to leave the inertia blank or 0. And then the assumption restrictions. The mass element has no effect on static analysis solutions unless acceleration or rotation is present. So that makes sense. If we don't put the gravity on it, the acceleration due to gravity on it, the mass element doesn't really do anything. Okay, so let's go back. Next thing we need to do is we need to specify the material properties, EX, PRXY, and the density. And then we'll do real constants and then section types. So let's start with the material properties. So come back out of element type, go down to material properties, or material props, go to material models, select on the right window here, structural, linear, elastic, isotropic. Okay. And then for EX, we need the Young's modulus. And again, we need to be mindful of the units. So it's 10,400 KSI, so we need to add 3 zeros to that to make it PSI. So it should be 10,400, and then add 3 zeros. 1, 2, 3 to that. And then PRXY is the Poisson ratio in the XY plane, which is 0.3. Click OK. And then next, look below isotropic. You'll see density right here. Click on that. And again, we want to give the density as a mass. And it's 0.098 pound mass. 0.098 pound mass per inch cubed. That's the density of the aluminum. Click OK. You should have two material models here. One's linear isotropic and one's density. And if you need to change these or confirm them, you can always click on one of them. It'll bring the window back up and you can change it and click OK. All right. So how are we doing so far? Any issues? Good. Okay, so that's our material models, our material properties. Next, we've got to give a real constant for that mass 21. So come back up to real constants, click Add, Edit, Delete, click Add. And then you want to be selected on the mass element, so type 2, mass 21. Click OK. And then we want to give the mass of 3.81 in pound mass for X, Y, and Z, mass X, Y, and Z. So 3.81 x, 3.81 for y, 3.81 for z. And then click, and then leave the inertials blank, and then click OK. All right, and then click Close. Good. So now let's give the two cross-sectional areas for the links. We'll start with the blue one at 0.81 inches squared. To do that, we come down to Sections and go to Link, and then click Add. And it'll ask you for the ID. Let's start with 1, the ID. Click OK. You can give it a section name. Let's go ahead and do that. We'll call it blue, for the blue section. And then for the link area, we're going to type in 0.81. And then if you had any added mass, like something was hanging on this, maybe a sensor or a cable, something like that, you can add some mass here. One thing you want to be careful is you want to double count the mass. You did already put the density in of the aluminum. This added mass is if you had something additionally added to it. And then here's our tension key. If you click on this, you can see you can choose tension or compression. You can see tension and compression. So we're just going to leave it as tension compression. It's a solid aluminum bar. You can push on it. You can pull on that bar. All right, so click OK. That's our first one. Go back on the left, click Add again. Change the ID number to 2. Click OK. Let's type the section number. Our section name is red, and then the area is 29. Yeah, 0.29. Then click OK. All right. Next, what we need to do is create our 10 nodes. So come out of Sections, come down to Modeling, Create Nodes in Active CS. Type Next in for the node numbers. One thing I want to show you guys, if you ever click up here and you start to lose that window, there's the Raise Hidden button here. I'll bring it back up top. Sometimes it gets stuck behind. Okay, so our first node is at 0, 0, 0. That's the origin. So 0, 0, 0. Click Apply. That's our first one. And then we're just going to follow down this list. Type all 10 of them. So node 2 is now at negative 34.86 in the X. $69.36 in the Y. And 0 in the Z. Hit Apply. Node 3 is negative 69.54 in the X. $80.92 in the Y. Negative 27.75 in Z. hit apply. $69.54 in the X again, 80.92 in the Y again, and then we just changed the Z to a positive 27. Hit apply. Node 5 is at negative 40.5 in the X. You can use Alt-Tab to go between windows and windows. I want to try to be fast about this. 90.248. I'm sorry, 9.248 in the Y. If you're using Alt-Tab, if you hold down an Alt-Tab, it'll show you all the windows. But if you just click it once, like Alt-Tab once, it goes to your previous window you had up. So that's 5. 6. You make the Z positive, 39.3, apply. Then we go to negative 69.54, 11.56 in the Y, and a negative 27.75. Apply. 8. 27.75 becomes positive. Hit apply. 9. The Y becomes 20.808. The Z becomes a negative 27.75. Hit apply. And then 10. The Z becomes a positive 27.75. And on this last one, I'm going to click OK. All right. And if you come back to ANSYS, you can rotate using Control on your keyboard and the right mouse button. And then go to List, Nodes, and click OK. You'll get a listing of all your nodes. Yep.
I accidentally added. How do I take what else?
Yeah, if you add an extra one, go to List, Nodes, and take a look at your listing, and make note of the node number you want to delete. Is it 11? Is it 11 in your case?
That's
3. So do you need to change 3 or do you need to eliminate it? Get rid of it? Yeah, okay. So come out of Create, go to Delete, click on Nodes here. You'll get this prompt, and you can actually click on the node, you can see it, or the easier way is if you look at the listing, you know the node number, you just type the node number here. So say it's 3. Type 3 in there and click OK, and it'll delete your node 3. And then what you can do is you can go back to List, Nodes, and you can confirm that you deleted all the nodes. Yeah. And one thing you'll notice, if you delete a node and then you make a new node, it doesn't fill in for the 3. It just appends to the last available number, so it'll go to 11. The node numbers don't really matter. It doesn't really matter the order of the numbers. It matters that you have the correct number of nodes. Did you have a question? Yeah.
So now that I deleted the first one, now I'm going to go 1, 2, 4, 5, 6.
Yep. Yeah, that's what I'm saying.
I just accidentally read this out of 0. So that bad.
Yeah. You just have to be careful with this step when you do elements. So so when you see a 3 in there, what you do
Well, no, so briefly, I tried to this 0, and then I realized I messed it up, so I redid the 4. Okay.
Windows is 11.
So this
Is it before?
All right, so it looks like most people have it, or everybody has it. Let's create the elements now. So the way that you create the elements is go back up to create. Now we're going to go down to elements. And before we start creating the elements, we need to set the attributes first, right? Because we have two different cross-sectional areas. We need to make sure the elements associated with the correct cross-sectional area. So we're going to start with that main strut, which is between nodes 1 and 2. So let's first set the element attributes. So click element attributes. And we need to make sure that the section number here is on blue. And then we need to make sure the element type is on a link element. You'll notice you have two element types. One's that mass element, and one's the link element. So make sure you have link 180 for that, and then the blue for section number. Click OK. And then come down to the next menu item, auto numbering. Click on through nodes. And it says pick or enter nodes defining the elements. So pick node 1, you can see it, and then node 2. Yep.
So if you can't see the nodes very well, can you just type in 1, okay, 2, okay?
Yeah, so what you would do, and we'll do this for the next elements, you would type 1, comma 2 into this prompt, or you can do 1 space 2, I think. But I usually put a comma in there. Yeah. So click OK, and it'll create the element. And again, if you're zoomed in too far and you just see a black screen, there's the fit view button here that'll bring you back out front. So once you create that first element, go ahead and zoom in and out on your screen. You should see it disappears. We showed this last lab. The reason why it disappears is because it refreshed the whole plot. If you click up in the upper left-hand corner where nodes plots, so when it refreshed, it only plotted the nodes. It didn't plot the elements. So in order to see nodes and elements, we have to plot the multi-plots. So go up the plot here, come down the multi-plots, click on that. You'll see E-N, which stands for elements, the nodes it's plotting. There you go. One thing you'll notice happens is that we lost our node numbers. We can add those back in by going to plot controls, numbering. Go to plot controls, numbering, and then come halfway down, you'll see node numbers. Switch that button on. Click OK. And there you go. So now we can see our node numbers, and we can see our element, our one element we drew. Okay, so let's work on the rest of the elements. So let's first change the element attributes. So click on element attributes. We're going to keep it on link 180, but we're going to change this blue to a red element. So change it to 2 red, the section number. Click OK. And then go down to auto numbering through nodes. And as your classmates suggested, we can actually type in the node numbers. If you deleted a node and recreated a node, you need to be careful with your numbering here. This is where you gotta, your node numbers are gonna be different than what I have here. Okay, so let's, for me, 1 to 6, 1 comma 6 is the next one I need to make. So 1 comma 6. Click apply to keep the prompt open. So there's 1 to 6. 1 comma 5 is next. 1 comma 5. 6 comma 7. Apply. 8 comma 5. Apply. 8 comma 2. Apply. 2 comma 7. Apply. 2 comma 3. Apply. 2 comma 4 next. Apply. 8 comma 6. Apply. 7 comma 5. 7 comma 5. Hit apply. 10 comma 6. Apply. And then our last one is 9 comma 5. 9 comma 5. And on this last one, we click OK. And again, you can hold down a control and the right mouse button and kind of see the structure a little bit better.
How do we do there? I said it because I just deleted all of them. I just re-put it and then I picked up 1, 2, 12, 13. One thing you do is go to the next step. Oh, you should have put one in there, then you type the 1, 2, and it'll put one.
One of the things we can do is we can color these elements based on their material properties. If you go to plot controls here, you go down to numbering, and then you go down to element / attribute numbering. You can put it, we can color it based on the real constant number. Right, so real constant 1 was the, well, actually, section numbers is what we want. Section number 1 was the blue section. Section number 2 was the red section. So if we put this as section numbers and click OK, you can see which elements are section 1, section 2. This kind of visually confirm that we have that correct. Another thing you can do to visually confirm it's correct is if you type up in the command prompt here, /E shape, comma 1, comma 1. So /E shape, comma 1, comma 1. Go ahead and do this. /E shape. E is an element. Comma 1, comma 1. Click enter. And then go to your plot and zoom in and out to refresh it. And it'll draw a square cross section that's proportional to the values that we specified in the section type. So you should see that the cyan section is a little bit larger diameter than the purple section. If we go to the command prompt again and we type in help, comma, /E shape, we can read about what this command does. So /E shape displays elements with shapes determined from real constants, section definitions, or other inputs. You'll see here it wants comma the scale, comma the key. If you read below here, if you put the scale at 1, use real constant section definitions or other information to form a solid shape display of the applicable element. And then if you put a 0 in for the scale, it'll use simple display of lines and area elements. That's the default value we're looking at. So if we want to turn this off, /E shape, comma 0, comma 0. So go ahead and turn it off for now. We'll turn it back on in a second. Put /E shape, comma 0, comma 0. And then again, zoom in and out on your screen, and you'll be back on the line representation of the elements. Okay, let's keep going. So we got to put some boundary conditions on this. So let's start with the displacement conditions. Those are going to be on the back 6 nodes that are on the plane of the aero body there, airframe of the lunar module body. So these 6 on this back plane here are going to get ux, uy, uz equal to 0. So use control and orient yourself in a view where you can see those 6 nodes. You can use the predefined isometric view. It'll get you close. And then you can use control and the right mouse button to kind of rotate to see it better. Okay. Come out of modeling. Let's go down to loads. Define loads, apply, structural, displacement, on nodes. We've got this prompt here. It says pick or enter nodes for displacement constraint. Click the 6 that are on that back plane. So 3, 4, 9, 10, 7, and 8. And you can rotate the figure after you have them selected to kind of confirm that they're all on that back plane there. Click OK. And then select UX, UI, UZ, and set the displacement value to 0. Yep. So 3, 4, 9, 10, 7, 8. 3, 4, 9, 10, 7, 8.
It's really close. It should be fine.
ISO, put your ISO down for a second.
You don't have well, that's fine.
So you have, let's see. Okay, so this connection here shouldn't exist. And you need a connection from 10 to 6. And this connection just shouldn't exist. This one should go from there.
All right, click OK. There. Now let's put our force on. So click force on nodes. Click the node at the origin. Click OK. Change Fx to Fy. And this force is going to be in the positive y direction. And the value is 16,500 pounds. Click OK. All right. And let's go ahead and solve this without the gravity on it. Let's take a look at some. Let's look at some values. So go out of preprocessor. Let's go to solution. Solve current LS. And then click OK. You should get solutions done. Hit close and close this window. And then come down to general post-processing. And let's look at plot results, deformed shape. And we can click on deformed plus undeformed. We can take a look at the deformed shape. So the dashed line here is the undeformed shape. Purple would be the deformed shape. And again, that's an exaggerated deformation just so you can see it. And then this DMX value here is displacement max. Saying the maximum displacement of the model, 1.36944 inches.
I don't see plot results under the general.
Did you run the solution? Go to solution. Solve. Current LS.
It never gave us solution. Yeah, so it's a lot.
On nodes. Then you're going to click read or 7.
I guess I've never said.
Solve it. That's fine. All right, so let's turn the D scale to 1. So again, this is an exaggerated scale of deformation. If you type in /D scale, DSCALE, comma 1, comma 1, and then you click enter, and then you refresh this plot. So you can either zoom in and out, or you can go back to the deformed shape and click OK. You'll notice that the deformation looks less exaggerated. So this is what you would actually see if we built this thing in front of us. Loaded up to 16,500 pounds. This is what 1.369 inches looks like that. If you go to the command prompt and you click up on your keyboard, so go to the command prompt and click up once, or click. Let's get it right. If you click down. Sorry. So delete the command and then press down. It'll go to your last command you typed in, and then change /D scale 1, comma 1 to /D scale 1, comma 10, and click enter, and then zoom in and out. So the last number on that is the displacement multiplier. Now we're exaggerating displacement 10 times the true displacement. So you can press down again. Let's do 100. What does 100 look like? Here's what 100 times exaggeration of the displacement looks like. So why is this useful? If you had some part of your model that wasn't moving much, but you wanted to see it, what direction it's moving, whatever, you can increase the displacement multiplier. See it moving. Let's change it back to D scale 1. So again, down, go to 1, enter. There you go. So I'm going to make note of a couple values here. So that's DMX values, our displacement max value. I'm going to make note of it here, 1.36944. Let's also get our reaction value. So if you come out of plot results, you go down to list results, you can get the reaction solution. Right here's reaction solution. Click that. And then let's get all the items, so click OK. You'll get a listing of our constrained nodes here. So 3, 4, 7, 8, 9, and 10. And then each of these 3 columns are the reactions in each 3 directions. And at the very bottom, it gives you the total reaction force. So notice it's basically 0 in the X, 0 in the Z, and then negative 16,500, which is equal and opposite to our applied load of 16,500. So I'm just going to make note of that total reaction in the y on my spreadsheet here, minus 16,500. Let's also answer question 1 since we got the plot pulled up. So we want to plot the deformed shape only, the true scale with the element numbers labeled. So if you go back to ANSYS, we have the D scale set to 1 already. That's good. But we don't have the element numbers on here. We have section numbers. All right, so we need to go back up to plot controls, numbering, and let's change section numbers. Scroll up on that listing to element numbers. All right, so element numbers is on. Click OK. It'll replot it. And the other thing we want is we want the deformed shape only. Currently we have undeformed and deformed. So go back to plot results, deformed shape, and change it to deformed shape only. Click OK. There you go. And what I like to do is I like to use a snipping tool. I'll snip this like this. I like to format my figures in PowerPoint. So what I'll do is I'll put the snipping in the PowerPoint. I'm going to put a sub-figure index on this. So that's going to be our sub-figure A. And now let's go generate it with the node numbers labeled. Element numbers off. So I'm going to go back to ANSYS, go to plot controls, numbering. Oh, I messed that one up. I had the node numbers on already. Let me recreate that one. All right, that's element numbers. Let's do the node numbers, plot controls, node numbers on, and then I'll turn the element numbers, then node numbering. Okay, there's our node numbers. Node numbers. First one's element numbers. And then you can use the snipping tool again if you like, or you can group them as a figure. I'll use the snipping tool again. And then go to Word. Insert a text box. paste this in the text box, and then below that I put figure 1. Actually, no, or that opposite. So I'd write a caption like that. Subfigure A is a plot of the element numbers. Subfigure B is a plot of the node numbers. So that's typically how I make a figure that has subfigures. I use PowerPoint. You can snip it once you format in PowerPoint, and then put it into Word. Let's look at the let's actually add gravity onto this. And one other thing we forgot is our mass element. So let's add our mass element, and then we'll add gravity. So let's go to modeling, create element attributes. Let's change the element type to a mass 21. And then let's change our real constant. No, we're good. Our real constant, we only have one of them. So let's change it to mass 21. Click OK. And then go to auto numbering through nodes. Let's click on node 1. And click OK. And we're done. We got our mass in there now. And again, if you don't have acceleration on it, the mass doesn't contribute anything to the problem. Okay, so let's add acceleration. Let's add Earth's acceleration to begin with, and we'll work on the moon's acceleration. So to add acceleration, I go to loads, define loads, apply structural inertia, gravity, and then click on global. And then you get this window here, and it's asking you for the acceleration in what direction. And this is kind of counterintuitive. What you got to think about is which direction do I accelerate the body to get the gravity vector in the correct direction. So what we want to do is we want to accelerate the body upwards in the y direction, positive y direction, to get a gravity force, or gravity vector, in the negative y direction. So we want that y component to be 32.2 feet per second squared. So when it multiplies times the mass and our density, and the mass and that mass element, we get a pound force applied to the structure. And this is where if you multiply density times acceleration, you would you multiply times acceleration already. We put 1 in it. It's at 32. So because we left this pound mass, we have to put the acceleration as 32.2. And then for the moon here in a second, what we'll do is we'll come back and put it in as 1/6 of that acceleration for the moon. All All right, so 32.2, we're going to accelerate the body upwards. It's going to create a force downward. Okay. And then let's go down to solution, solve current load step again. Go ahead and solve it. Click OK. We get solutions done. That's good. And let's go take a look at the results. So go to General Post-Processing. Let's plot the results again. So you'll notice the displacement is now 1.34029. So displacement actually went down slightly. Right, so if you think about it, we have a force upwards here, 16,500 pounds. And then we have these forces due to the mass of each of the elements. Right? And then we have a mass element here, so it also has a component downward. So these forces counteract the applied force in the negative y direction. All right. So these forces counteract 16,500. That means basically the applied forces decrease. Right? So you expect less deformation of the structure, the applied forces. And we should be able to confirm this with the reaction forces. So if you look at the reactions at these walls, it should be less. Let's go ahead and do that. So let's go to list results, reaction solution, click OK. And there it is, 15 minus 15,605 is the weight that the supports on this side of the structure have to support. That's the support less weight because its applied force is counteracted with the dead load. Right, and it's about 895 pounds less in that reaction force. All right, so let's go and apply Moon's gravity, and then we'll complete the questions out with the Moon's gravity. So go back to preprocessor, go to loads, go back to apply loads, structural, inertia, gravity on, and then global, and then we can change 32.2 to 32.2 divided by 6 for 1/6 Earth's gravity. And one thing you can do is you can do simple arithmetic in these entries. You can do divisions, multiplications, addition, subtraction. Instead of having to calculate this offline, you can just do 32.2 divided by 6. Click OK. Now go back to solution. We need to resolve it. So go to solve, current LS. Click OK. Solution's done. Close out of that. And let's take a look at the displacement. So plot results, deformed shape. We get 1.36458 for the displacement. So it's a little bit less than no gravity. So again, those are forces due to the dead load of the materials is helping us a little bit. Let's look at the reaction force, list results, reaction solution. 16,351. So it's about 149 pounds on the moon. On Earth, all the mass to the aluminum and the mass at the end there is 895. On the moon, it'd be 149. Okay, so let's answer the rest of the questions. So the third question here is copy the table of nodal displacements into your report, put it into a text box similar to your figures, include a caption, and we want to highlight the node with the maximum vector sum displacement. So let me show you how to get the nodal displacements. So we're going to go back to list results, nodal solution. Let's go to degree of freedom solution, displacement vector sum. Click OK. And you'll get a listing of all the nodes. They're UX, UI, UZ. And then the U sum is the square root of the UX, UI, UZ. Right. And then at the very bottom, they give you the maximum absolute value of each of the columns and the associated node that has the largest value. So it's saying node 1 has the largest maximum absolute value, which would be this value right here. Node 1 also has the maximum absolute value in Y. Node 5 has the maximum absolute value in the Z. And then the vector sum is just 1.3646, which we saw as the DMX value. The DMX value is the vector sum, max absolute value. All right, so to include this in your report, you can highlight this text. You can hit Control-C on your keyboard, go to your report, insert a text box again. Paste the text into the text box. Change your font back to the default font. Oops. Yeah. So figure 2, listing of the nodal displacements. And you can add like an additional detail here if you want, the maximum vector sum displacement was at node number 1 with a value of 1.3646 inches. And then the problem statement said to highlight the node with the maximum vector sum displacement. So what you can do is you can highlight node 1 here, like this. And then if you right-click your highlight, you'll see the text highlight tool. And click that, and it'll highlight the text. So that's what I'm looking for that question. I guess there's one additional detail here. So also report the location of the maximum. So report the maximum vector sum displacement at the top of the main stroke, which is node 2, which would be right here. It's 0.348. So we can also add that in. And you would also reiterate that in your paragraph. All right, question 4, plot a contour plot of the von Mises shape. Yep.
Do we just need that table for the moon, or should we go for Earth as well?
Just for the moon. And just to remind you, nothing's due, so this is just kind of showing you what I would expect, for these questions. So question 4 is plot the contour of the von Mises stress with E shape turned on. So pay attention here, this is something new. So we know how to turn E shape on. So E shape, comma 1, comma 1, go ahead and type that in. Click enter. If you zoom in and out in your figure, you'll see the E shape show up. And now if you want to see the stress, you have to have E shape turned on to see the stress here. We want to come down to result viewer. Click on that. You'll get this new window to show up where it says choose a result item. Click on that. And then go down. You'll need to collapse nodal solution and click on element solution. You'll see stress there. And then go down to, keep scrolling down, you'll see von Mises stress. And then you want to click this little symbol once you have that selected. It says plot results. First icon on the right there. And there you go. So again, the stress is uniform throughout the element because it's a two-force member. It's the uniaxial force divided by the cross-sectional area. The two elements with the highest stress have a little mx next to them. And their contour color is red here. It's these two up here. The lowest stress is in the blue here. It has a little mn next to it. If you look up on the upper left here, you see dmx here. That's the displacement max. If you see below that, you have smn. That's the stress minimum, 8,816.44 psi. smx is a stress maximum, so 38,929.4 psi. Right. And we can use our snipping tool again. We can snip this. We can close out of here if you like. It'll show up in the main window. You can insert your text box. Add your caption. So since we have this plot of element numbers, the two elements with the maximum stress are element 8 and 9. Okay, so that's the contour plot. Next, question 5. This is a pretty important one. Copy from the table of elemental stress from the listing for the element with the maximum stress. I'm going to put the output in a text box with the caption. I say do not copy the whole outputs. Copy only the elements with the maximum von Mises stress. So we know visually it's 8 and 9. Let's go find it in the listing now. So if I go to general post-processing and go down to list results, you can go to element solution here. And again, go to stress, von Mises stress, OK. And here's the listing of the stresses. And again, this can get pretty large if you have a large number of elements. What we want to do is we just want to copy the two elements that have the largest stress. If you look here, notice they're grouped in the elements. So here's the element number, element 1, and then these are the two nodes that make up that element, node 1 and node 2. The columns here labeled S1 are this is the first principal stress, S2 is the second principal stress, S3 is the third principal stress. S int is the stress intensity, and then S equivalent is this equivalent stress, which is also known as the von Mises stress. So what we want to do is we want to look down this last column and look for the highest value. So we got 25,000 starting off here, and then it goes to 22, then it goes to 29. So 29 is our highest now. 29, 27, here's 38, 21, 8,000. So this 38 is the highest stress. Notice this for element 8, and then element 9 is a symmetric element, symmetric in the structure. It's on the other side of the plane of symmetry, so it sees the same exact stress, 38,000. So what I'm going to do is I'm going to copy these two. Depending on the problem, there might not be two. It might just be one element that has the highest stress. But in this case, because it's symmetric, we have two elements with the same. So I'm going to copy both those elements. Go to my Word document, put a text file in. Again, we can paste. If you hit Control-C on that, you can Control-V it inside of here. Here's our figure 4 now. The maximum stress is in element 8 and 9 with a value of 38.9 KSI. All right, and there's one additional comment here where we have to state where the location of the element is using figure 1b. So I'm going to say these elements are located at the very top of the LM landing structure. All right, we're almost there. Question 6. If the yield stress of 7075 is 76.1 and the required safety factor is 1.15, does the structure pass this criteria? So we just record the value at 38.9 KSI. 38.9 KSI, that's the maximum stress we're getting. 76.1 is the yield stress of 6061 T6 aluminum. So if I take 76.1 divided by 38.9, I get a value of 1.95. So our safety factor is 1.95, which is greater than 1.15. So the structure passes the criteria, won't fail. So we're good. All right. Let me pause for a second. Anybody have any questions so far? All right, so let's attempt this last question. So it's going to be to conduct a transient problem with the force applied at time is equal to 0, and we want to run it for 10 seconds. Look at the response to the structure. Yep. Yep. Yes, it's something that's good to look up at the Wikipedia page. They have the equation there. Yeah, so the factor of safety is defined as the yield stress divided by the working stress. So the yield we get from the material properties, 76.1 is the yield point of aluminum, 6061 T6 aluminum. And this working stress is the value we're getting from ANSYS. So if it's 76.1 divided by the value we got from ANSYS, 38.9, I got a factor of 1.95 in there. Does that make sense, this equation?
So the one ANSYS 38.9 is the working?
Yep. And then the yield stress is this for the material properties. So you can get that from, remember materials lab, like putting the samples in the machine. All right, so let's try this last problem with our last 10 minutes. So we're going to apply we have a force on this, and we have gravity acceleration on this. We're basically going to apply this thing as a step function. So if you have force on the y-axis and you have time on the x-axis, what the applied force looks like is it's going to be, this is time equals 0 right here. So time equals 0, we're going to turn on the force like this. It's going to be held infinitely. Right? So we'll say maybe this is a 10 second mark. And then if we had a similar plot of displacement, say displacement is x, this, we want to look at time equals 0, how the structure responds to this applied load. It's going to do something like this, right? It's going to oscillate. It's not going to instantaneously, as soon as you apply the load, it's not going to instantaneously hit that deformation, right? It's going to take some time. So, and there's no dampening in the system, so this thing is it's just going to ring forever, basically. Okay, so let's give it a try. So go to solution. Go to analysis type, new analysis. And then you'll see all the possible analysis we run. We want to run a transient analysis. So a function of time. Click OK. Click OK again. And then go down to solution and controls here. And we need to specify the end of the load step. So that's how long we want to run the simulation for. We'll put 10 in there for 10 seconds. We also want to tell it the number of sub-steps to take. So this is basically how many times we want a result printed out. Let's do 100 for sub-steps. So it's going to give us a result every 10th of a second. And then over on the right-hand side, we got to tell it when to save these results. And if you click on this down menu, you scroll up on it, you want to click on write every sub-step. So every 10th of a second, I want to save a result. Okay, click OK. And then go to solve current LS, and then click OK. It should solve pretty quick. Solution done. Close. All right. And then let's now go down to time history post-processing. Click this plus right here. It says add data. And then click degree of freedom solution. Let's look at the Y displacement. Click on Y displacement. Click OK. And then we got to move this thing off to the side for a second and click on the node that's at the origin. So we want to mod it. We're going to plot the displacement of the Y and the Y of this node at the origin as a function of time. So click the node right there. And then click OK. All right, you should see something show up here, UY_2, and then click this button. It's a black icon with the cyan line on it. It says graph data if you hover over it. And then you got to move this thing off to the side again. So this is what the response of the structure looks like. It looks like this. It's kind of bouncing up and down. It's actually going positive, negative, when you apply this load. So this tells you need to add some dampening to the system. There'll be some natural dampening just because these connections are a little bit loose. Right? There'll be friction in these connections, which adds dampening to the system. This is why if you look at the bridges in like Pittsburgh, they use rivets. They don't weld everything because these lap joints actually provide friction and dampening to the bridge. So when a car goes over it, it doesn't resonate out of control. There's actually a loss associated with the steel plates rubbing against each other. Okay, so this is what it's doing. So this node is going, when you apply the force here, it's going to shoot up to 1.5, which is actually greater than our equilibrium displacement, like 1.36, right? When you go past that, it's like, oh shoot, now it's going to come all the way back. The negative points, actually it's positive 0.8, and it's going to go 1.37. It's going to start vibrating like this, up and down, up and down. And it's going to do this forever. We can take a look at this if you want to see the animation of this thing vibrating back and forth, if you go back to general post-processing and you come down to result viewer, and let's look at nodal solution, degree of freedom solution. Let's look at, I don't know, the y displacement. That's our y displacement. Right now it's plotting for 0.1 seconds, our first time step. You can actually slide the slider around and it'll change the value. You'll see, like, now we're at 4.3 seconds. It's moving a little bit. But you can click this button right here that has the, looks like it's shaking. The contours are shaking. Click on that. You can animate over the results. And then you can specify, you know, what range of the results you want to do. If you just leave this blank, it'll do all the results. Here's the increment of result sets. So it's going to do every one. And then you click OK. You can slow this down if it's too quick. If you want to speed it up. You can take a look at it. Again, we're applying this force 1650 as a step function. It's a structure response. It's trying to find its equilibrium point, but there's no dissipation of energy. It's just going to kind of reign there forever. So once you create that animation, you can actually find it in your working directory. Documents 2. You'll see this assignment 2 ABI. We can save this. Well, it should run. Let's see if they have DLC player. So you can look at that offline outside of ANSYS. All right. So that concludes the lab for today. Anybody have any questions about the lab? Don't worry too much about the training stuff. We're gonna